It's now eligible to organize these of the game Paragon. abilities, activating those abilities, handling notifications. Welcome back. So now that we have some sort of idea what the gameplay ability system is, we need to know the different parts that make up the system. So we'll discuss those in this video and lay out a plan for the next steps moving forward that we can take to start adding gas to our project. Now, one of the most important parts of gas is the ability system component. This is a type of component that can be added to an actor, and it handles lots of important things in the gameplay ability system, such as granting abilities, activating those abilities, handling notifications for when certain abilities are activated or effects are applied, and lots of other things that we'll learn about. So the ability system component is something that we must add to our character if we'd like that character to participate in gas. Now, just as important as the ability system component is the attribute set. Just about any game involves a number of attributes that you associate with any given object or character, and these range from life and mana to just about any other attribute that you can think of. In gas, we store these attributes on the attribute set, which has a number of capabilities that allow us to associate those attributes with other various parts of the gas system. Now, at the core of the gameplay ability system are the abilities. Gameplay abilities are classes that we use to encapsulate the functionality of some sort of thing that a character or object can do in the game. Things like attacks and casting spells are generally abilities, and the gameplay ability allows us to keep all the code and functionality kept inside of a specific gameplay ability class. Now, gameplay abilities run asynchronous tasks that we call ability tasks. These allow us to execute code that is asynchronous, meaning that once we start the task, it may perform its job and finish immediately, or its job may span across a period of time and may do different things depending on what's going on in the game for that specific ability. So ability tasks are like the workers that perform the work for the gameplay ability itself. Now, we also have gameplay effects. These are what we use to change the values of attributes, and they're capable of a number of different things related to attributes. We use gameplay effects to change attributes directly, change them over time, periodically increase or decrease them, and associate those attribute changes with various calculations that take other parameters and attributes into account. We also have gameplay cues. These are responsible for handling cosmetic effects, such as particle systems and sounds, and can handle the replication of those as well. Now, another core part of the ability system are gameplay tags. Now, gameplay tags are not actually unique to the gas system. They exist outside of gas and can be used in non-gameplay ability system projects, but their use is pervasive all throughout gas, and gameplay tags are extremely useful for identifying just about anything you can think of, and their hierarchical nature makes them more versatile than simple variables such as enums, booleans, or strings. And we'll learn all about their usefulness throughout the course as we use them. So these are the main parts of gas, and we need to start with the first two of these in order to incorporate gas into our project. We need an ability system component and an attribute set. Now, the way that we add an ability system component can vary. We can have a pawn, and in the case of our project, our player-controlled pawn is an aura character. And you can add the ability system component directly on the pawn class. You can do the same thing with the ability attribute set. Now, the way that we add these main parts of gas and adds or strings, and we'll learn all about their usefulness throughout the course as we use them. Now, gameplay tags are not actually unique to the gas system. They exist outside of gas and can be used in non-gameplay ability system projects, but their use is pervasive all throughout gas, and gameplay tags are extremely useful for identifying just about anything you can think of, and their hierarchical nature makes them more versatile than simple variables such as enums, booleans, or strings. And we'll learn all about their usefulness throughout the course as we use them. So these are Welcome back. So now that we have some sort of idea what the gameplay ability system is, we need to know the different parts that make up the system. So we'll discuss those. Welcome back. So now that we have some sort of idea what the gameplay ability system is, we need to know the different parts that make up the system. So we'll discuss those in this video and lay out a plan for the next steps moving forward that we can take to start adding gas to our project. Now, one of the most important parts of gas is the ability system component. This is a type of component that can be added to an actor, and it handles lots of important things in the gameplay ability system, such as granting abilities, activating those abilities, handling notifications for when certain abilities are activated or effects are applied, and lots of other things that we'll learn about. So the ability system component is something that we must add to our character if we'd like that character to participate in gas. Now, just as important as the ability system component is the attribute set. Just about any game involves a number of attributes that you associate with any given object or character, and these range from life and mana to just about any other attribute that you can think of. In gas, we store these attributes on the attribute set, which has a number of capabilities that allow us to associate those attributes with other various parts of the gas system. Now, at the core of the gameplay ability system are the abilities Gameplay abilities are classes that we use to encapsulate the functionality of some sort of thing that a character or object can do in the game. Things like attacks and casting to encapsulate the functionality of some sort of thing that a character or object can do in the game. Things like attacks and casting spells are generally abilities, and the gameplay ability allows us to keep all the code and functionality kept inside of a specific gameplay ability class. Now, gameplay ability abilities run asynchronous tasks that we call ability tasks. These allow us to execute code that is asynchronous, meaning that once we start the task, it may perform its job and finish immediately, or its job may span across a period of time and may do different things depending on what's going on in the game for that specific ability. So ability tasks are like the workers that perform the work for the gameplay ability itself. Now we also have gameplay effects. These are what we use to change the values of attributes, and they're capable of a number of different things related to attributes. We use gameplay effects to change attributes directly, change them over time, periodically increase or decrease them, and associate those attribute changes with various calculations that take other parameters and attributes into account. We also have gameplay cues. These are responsible for handling cosmetic effects, such as particle systems and sounds. and can handle the replication of those as well. Now, another core part of the ability system are gameplay tags. Now, gameplay tags are not actually unique to the GAS system. They exist outside of GAS and can be used in non-gameplay ability system projects, but their use is pervasive all throughout GAS, and gameplay tags are extremely useful for identifying just about anything you can think of, and their hierarchical nature makes them more versatile than simple variables such as enums, booleans, or strings, and we'll learn all about their usefulness throughout the course as we use them. So these are the main parts of GAS, and we need to start with the first two of these in order to incorporate GAS into our project. We need an ability system component and an attribute set. Now, the way that we add an ability system component, more versatile than simple variables such as enums, booleans, or strings, and we'll learn all about their usefulness throughout the course as we use them. So these are the main parts of GAS, and we need to start with the first two of these in order to incorporate GAS into our project. We need an ability system component and an attribute set. Now, the way that we add an ability system component can vary. We can have a pawn, and in the case of our project, our player-controlled pawn is an aura character. And you can add the ability system component directly on the pawn class. You can do the same thing with the attribute set if you like. Now, another option, learn all about their usefulness throughout the course as we use them. So these are the main parts of GAS, and we need to start with the first two of these in order to incorporate GAS into our project. We need an ability system component and an attribute set. Now, the way that we add an ability system component can vary. We can have a pawn, and in the case of our project, our player-controlled pawn is an aura character. And you can add the ability system component directly on the pawn class. So these are the main parts of GAS, and we need to start with the first two of these in order to incorporate GAS into our project. We need an ability system component and an attribute set. Now, the way that we add an ability system component can vary. We can have a pawn, and in the case of our project, our player-controlled pawn is an aura character. And you can add the ability system component directly on the pawn class. You can do the same thing with the attribute set if you like. Now, another option is to take some other class associated with your pawn, such as the player state, and add the player. So I think it's about time we start to discuss multiplayer and its relationship to the GAS system. Now, in a multiplayer game, there exists a server, and in most cases, just one server. And this server is an instance of the game running separately and independently from the other machines that are also running their own version of the game. We call those clients. Now, the server is different than the clients, and we're going to discuss those differences in this video. Now, in a multiplayer game, the server can take on a number of flavors. For instance, there's the dedicated server. A dedicated server has no human player, and no rendering to a screen occurs. It's just a computer running the game simulation. Now, because there's no human player and no actual rendering to a screen, Welcome. Now, so far, there have been a couple of times that we've thrown a couple terms around that have to do with multiplayer. So I think it's about time we start to discuss multiplayer and its relationship to the gas system. Now, in a multiplayer game, there exists a server, and in most cases, just one server. And this server is an instance of the game running separately and independently from the other machines that are also running their own version of the game. We call those clients. Now, the server is different than the clients, and we're going to discuss those differences in this video. Now, in a multiplayer game, the server can take on a number of flavors. For instance, there's the dedicated server. A dedicated server has no human player, and no rendering to a screen occurs. It's just a computer running the game simulation. Now, because there's no human player and no actual rendering to a screen, don't let that fool you into thinking that things are not happening on the server machine, such as players running around, shooting each other in a shooter game, casting spells in a magic game, leveling up and gaining experience, and things like that. Those are all things that can and do happen on the server version of the game. They just don't happen to be showing that by rendering images to a screen, as the server doesn't need to do that. Now, aside from the dedicated server, there's another type of server model called the listen server. Now, this differs from the dedicated server in that the listen server is a human player, or at least it's a computer running a version of the game on which a human player is controlling a pawn or character. We say that that human player is hosting the game. Now, the host has an advantage in the listen server model, and that advantage is that the host has no lag. Lag is the result of the time that it takes for data to travel across the network from the server to clients and from the clients up to the server. In a listen server, the host is the server, and the server doesn't have to send data across the network to itself, so there is no lag for the hosting player. Now, in Unreal Engine, we treat the server as the authoritative version of the game. Things are happening on each machine. Players run around, they change their positions, and this happens on each in every version of the game that's running. But because of lag, your version of the character's location on your machine is going to be different than your character's location on another player's machine and on the servers. So we have to decide which machine is the correct version. We consider the server to be the correct version of the game. And for this reason, we do important things on the server. Now, what are those important things? We'll learn about those as we go along and program the game, but it's important to know that the server is always considered the authoritative version of the game. Now, if we draw a dotted line between the server and the clients, we can make some distinctions about certain game classes. The game mode exists only on the server. If you attempt to access the game mode on one of the clients, you will get a null pointer. That's because the game mode is responsible for things like rules of the game, spawning players and restarting the game, things like that, and those are some of those important things we were talking about that should only be handled on the server. Now, the player controllers for each player exist on the server, but they also exist on each client. So the server has an authoritative server version of each player controller, and each client has their own local version. But notice the client 0 only has player controller 0 on its machine. There is no player controller 1 or player controller 2. All the other player controllers don't exist on client 0. It's only the server that has all of the player controllers in the game and can access them. Now, the player state is another story. The player states for each player all exist on the server, but they also all exist on each client. Client 0 has a version of player state 0 along with player state 1 and player state 2. So that's a distinction from the player controller class. Now, if that seems confusing, just think of it as a sort of similarity that the player state has with the pawn. You see, the server has all 3 pawns in the game, but each client also has all 3 pawns in the game, which makes sense. If you're playing the game, you have to be able to see your pawn running around, but you also have to see the pawn controlled by client 1 and the pawn controlled by client 2. It only makes sense that your machine has copies of all 3 pawns in the game. Same with client 1. It needs to see your pawn as well as its own and client 2. The same goes for the player state. Are sort of different than all the other classes and client. If it's a listen server, then the only HUD that exists and only has its for that player. Client 0's machine. We set our was set to have frequency just means that as changes are made on the server, it can be informed of that needed on clients. From the server down to clients, we call that replication. And here's how it works. Or any other type. Now, it exists in the pawn, the version of the pawn on that other type is the on the machine. So what does all this mean in relation to playing the game? The same goes for the player state. Now the HUD and all associated widgets that get shown on the screen are sort of different than all the other classes. Each client has its own HUD class, and it only exists on that client. So if we're talking about a dedicated server, there is no HUD on the server. If it's a listen server, then the only HUD that exists is the HUD for that local player playing the game. Each client only has its own HUD and any associated widgets that get shown to the screen for that player. Client 0 does not have access to client 1's HUD. It doesn't exist on client 0's machine. So what does all this mean in relation to replication? We set our player controller class to be replicated. What does that mean? And our player state was set to have a net update frequency of 100. What does that mean? Well, net update frequency just means that as changes are made on the server, every single net update, the server sends data down to the client so they can be informed of that change. A net update frequency of 100 means that those changes will be updated on clients 100 times a second as long as the server can manage that. When data is transmitted from the server down to clients, we call that replication. And here's how it works. Let's say you have a variable on the pawn class. Now, it could be a float, an integer, or any other type. Now, it exists in the pawn class, which means that each version of the pawn has that variable. The version of the pawn on clients, the version of the pawn on the server, they all have the variable. Now, if the variable is designated to be a replicated variable, then if that variable's value changes on the server, then the next net update, that change will be sent down to all clients so that the client version of that variable can be updated to the new value. This act of sending that data down to clients is called replication. Now, what happens if we have a replicated variable and it gets changed on one of the clients? Does that mean that the server will be informed of that change? In other words, does replication work both ways? The answer is no. Replication only works one way, from server to client. So if a variable is marked as replicated, it should not be changed on clients because the server will not know about that change. And neither will any of the other clients. Only the client who changed that variable will know about it. And that variable will now be out of sync with the server's version of that value. And remember, the server is the correct version. So the variable on that client will now be considered incorrect. Now, you might be thinking, if replication only works one way, how would a client ever get data up to the server? Obviously, that has to happen sometimes, right? I mean, we make input with our keyboard and mouse or controller. That input has to make its way to the server somehow. Well, yes, it does, in the form of replicated functions, which we call RPCs, or remote procedure calls, and we'll learn about those later. But the truth is, this high-level overview of replication is just about all you need to know about multiplayer for this course. You can learn all about it if you take my multiplayer shooter course, but there's a reason that course is not a prerequisite for this course. And that's because most of the multiplayer stuff is handled under the hood for us in GAS. We will need to know a little bit about multiplayer, but for the most part, GAS handles a lot of stuff for us under the hood. And we'll learn about that stuff that GAS does for us so that we can appreciate and let it work for us as we're building our game. And all of the gameplay mechanics that we implement in this course will work in multiplayer as well as single player. So now that we know a little bit about how the classes work in relation to multiplayer, we'll now move on and add our ability system component and attribute sets to our player state for our player-controlled character and to the character class for our enemies, and we'll learn how to associate the ability system component and attribute set with its owner, and we'll learn what that means in the videos to come. I'll see you soon. Okay, so we're ready to actually add our ability system component and game projects, health, and other important attributes are displayed. Welcome. So our game project involves attributes, such as health, and in nearly all game projects, health and other important attributes are displayed to the player on the screen. We refer to objects displayed on the screen as widgets, and in Unreal we create widget blueprints to provide visual representations of game data. Widget blueprints are derived from the base C++ class useWidget. Widget blueprints need to receive data. A health bar needs to know how much health to display. An icon for a given ability needs to show the correct icon for that ability. The point is that widget objects must receive data so they know the correct values to depict. And the game is rife with this data. The attribute set contains numerical data for all of the attributes belonging to a given character. The player state might contain a number of variables that need to be shown to the player on the screen for any number of reasons. There are numerous classes in the game, each containing data that may or may not need to be known by the widget objects in order to show the player what's happening behind the scenes of the game mathematically. So the question arises, how should the widget object get that data? There are a number of ways. The widget object could manage to dig its hands deep into the game code, retrieving pointers and references to the characters, controllers, player states, ability system components, attribute sets, and access all that data it needs directly. But is this the best way? As you're making your game project, the question should arise in your mind, how should this type of system be designed? As the game grows in size and complexity, how should this type of data be handled? How would, say, an experienced developer do it? How do AAA games do it? That's what we're concerned with in this course, how to do this in a scalable and maintainable manner. Now, in a well-structured program, we should have a separation of concerns. With UI, we have 3 different domains. The first domain is the display of visual effects of the data, such as health bars and ability icons, basically all your widgets. We'll call this domain the view, as it contains all the things the player views while playing the game. Now, we also have the data itself. These are the numerical values, the player's health, the player's level, mana, experience, which abilities have been unlocked, what their levels are, and what buttons those abilities are assigned to. All this data exists within the codebase of the game project itself, and we'll call this data the model, as it models the underlying rules and results of the game. This is the data that will ultimately drive the widgets that we will see in the view domain. Now, getting data from the model to the view is a task we need to think about. This can be done in a number of ways, but a good way to organize this is to have some sort of class that can handle retrieving the data from the model and broadcasting it to the view. This class can be responsible not only for the retrieval of the data, but any calculations or algorithmic functionality involved in processing that data. This class exists in a domain that we'll call the controller in this system, and the controller will be responsible for retrieving data from the model and passing it to the view so it can depict data visually. Now, we're not talking about the A controller or A player controller classes in the engine. Those are designed to possess and control pawns. What we're talking about is a controller class used to drive data to the view. So for that reason, we'll refer to this as a widget controller. This means the view can simply focus on how the data should look, receiving the data from any broadcasts made from the controller. But the view may contain widgets that the player can interact with, such as buttons. When the player clicks a button, that action may result in some change in the model, such as increasing attributes or granting new abilities to the player. So the controller's job is also to facilitate the actions resulting from the widget interaction by the player, causing changes in the model. In other words, the controller is a middleman between the view and the model. Now, some implementations of this software architecture pattern are different than others. Sometimes the widget controller is only responsible for retrieving data from the model and presenting it to the view. But for our project, the widget controller is going to have a little bit more responsibility in that it'll handle button presses and information that the player will provide and actually send signals out to the model so the model can make changes. With the model view controller architecture, we have 3 separate concerns, and each domain is isolated from the others, which makes the system highly modular. It prevents us from hard-coding dependencies that would render the system rigid. Our model shouldn't ever need to care about which controllers or widgets are being used to represent their data. It's the controller itself that depends on the classes in the model. The controller should never need to know which widgets are receiving data broadcast to them. It's the widgets that depend on the controller. And if we maintain these one-way dependencies, then the model can have its widget controller changed out for other widget controllers without needing to change any code in the classes in the model. Likewise, the controller shouldn't need to know what types of widgets the system has, as it's the widgets that depend on the controller. This way, the controllers can have their widgets switched out as well, without changing any code in the controller. And now we have a code base that's flexible and well-coded. This is the type of system we'll design for this game project, and we'll see the benefits of such a system as our project grows in complexity. Our controller can be a simple U object, and we'll give it the ability to harvest data from the system and broadcast it to the widget. And we'll create a subclass of the user widget that will be compatible with our widget controller class. So our next steps are to create this architecture for the UI in our game. We'll want our own custom-based widget class, which we'll call UAura user widget. We'll make the widget controller class, UAura widget controller, and we'll want to subclass the HUD as well, so we can have a location where these classes can be constructed and initialized. Once we have the system in place, we can go about harvesting and broadcasting data in the widget controller, receiving it in the widgets we create that can display visuals in the view, and we'll be able to see the health and mana attributes With the model view controller architecture, we have in that it'll handle button presses and would render the system rigid. It's the widgets that depend on the controller. And if we maintain these one-way dependencies, widgets the system has, this is the type of system and complexity. Our controller can be a simple U object, and we'll give it the ability to harvest data from the system and compatible with our widget controller class. Base widget class. So our next steps are widget controller class. Welcome back. Now we're adding our Welcome back. Now that we have our widget controller, I'm going to go to Aura HUD here and just take a look at an overlay. We know we have a widget controller on our overlay widget. And the overlay widget has a handle to the widget controller. It has a pointer variable. And we can access that. We've seen that we can even access it from Blueprint. Now, the widget controller doesn't know anything about the overlay widget. All the widget controller knows is that it has access to the 4 key variables. That's how it's going to access data to broadcast to the widget. And when we say broadcast to the widget, we are talking about delegates, because delegates are a great way to have one-way dependencies where our widget controller doesn't know about the widgets that it's broadcasting data to. The widgets know about the controller. That's the way that it goes. So our widget controller should have a way to broadcast initial values, such as the initial health and the initial mana values for those mana and health globes. So our widget controllers all are going to want some sort of way to broadcast initial values. So for that reason, I'd like a function in the base widget controller class or a widget controller to broadcast initial values. So I'm going to make a public function here for just that. So we'll make this a virtual function, void, and it will be called broadcast initial values. And any widget controller that inherits this function should be able to broadcast its own unique initial values, but they're all going to have this function. And I'm going to go ahead and generate the definition, but it'll be empty here for the base class or a widget controller. We're just going to use it in classes that derive from it, such as our overlay widget controller. And I'd like to override that now. So we're going to go to overlay widget controller.h. We're going to make a public section, and we'll override that function, virtual void, and it's going to be broadcast initial values. That's an override, and we'll generate that definition. No need to call super. Super is empty. We're just going to put our own broadcast. Now, what are we going to broadcast? Well, we know that we have health and mana. We need to broadcast some values to those widgets. And for that reason, I'd like to create a couple of delegates for broadcasting those values. So let's keep this a bit cleaner. Let's go ahead and right-click and close other tabs. And I'm going to Alt-O, Control-K-O in Visual Studio to open overlay widget controller.h. And I'd like to add a couple of new delegates. I'd like to make these dynamic multicast delegates. I'd like them to be dynamic multicast because, for one, I'd like to assign events to them in Blueprint, in our widget blueprint specifically. That's why I want them to be dynamic and multicast, because multiple widget blueprints may want to bind to these delegates so that they can update. So we're choosing dynamic multicast. So we're going to say declare _ dynamic multicast delegate, and we have several flavors. We're going to want one with one param. Why? Because we want to send a value out through the delegate. So we want to broadcast the health value. So we need to pick a name for this delegate type. It has to start with an F, and I'm going to call this on health changed, but I'm going to add signature at the end of it. You may have seen this on some delegate types in the engine. They put signature at the end. That's just to specify that this is the delegate type, and this one is capable of sending a single parameter. It's going to be a float, and it's going to be the new health. So we're declaring a delegate that can broadcast a float, and this is going to be designated for the health specifically. Now, I'd like to make another one for max health. I want to broadcast the values of health and max health as they change separately. So for this one, we'll call this F on max health changed signature, and we'll say this is called new max health. Now, this just declares the type. We want a couple of member variables of these types that we can assign in Blueprint. So we're going to come down here into the public section in the widget controller class and make a couple of these. We're going to make an F on health changed signature, and we're going to call this on health changed. So this is why I didn't call this F on health changed and then create an on health changed. The signature makes it clear that this is the delegate type, and then on health changed is the delegate itself, and we're going to give it a U property. And I'd like to be able to assign to this in Blueprint, so we're going to make it Blueprint assignable. And we'll go ahead and give it a category. And this is related to gas. So I'll have gas, and I'll use the vertical line, half of the logical OR, right? And we'll have a subcategory attributes. That's where this will be. And because we made a dynamic multicast delegate and we made it Blueprint assignable, then we can bind to this delegate in Blueprint. And that's where I plan on binding to it. Now I'm going to do the same thing for our max health variable. So we're going to have an on max health changed delegate as well. And once our widget blueprint, our WBP overlay, or our WBP health globe, or our WBP mana globe, any of those, our widget blueprint, our WBP overlay, or our WBP Health Globe, or our WBP Mana Globe, any of those, if they have access to the widget controller, they can assign an event to receive that health if we broadcast it. So this is great. We have 2 delegates. Now we need to broadcast the initial values. So what that means is we need to take these delegates and broadcast some value, right? We need to take on health changed and call dot broadcast. That's how we do it. And we can broadcast 100.f, right? But, well, what if this is wrong? What if our attribute set doesn't have the health value initialized to 100? What if it's a weaker type of character class? What if it starts off at 50 or 65? We can't be hard coding things like this. We need to get the actual value of the health attribute, right? How do we do that? And that's going to be your quest. I'd like you to figure out how to get the actual health attribute in broadcast initial values and, well, broadcast it. Broadcast both the health and the max health. So pause the video and do this in broadcast initial values now. Okay, so here in broadcast initial values, we don't want to just broadcast 100 attribute based on Aura, the attribute set. It's a T object of the Aura attribute set. So let's do the header for me. That's a pointer, and now we can use cast checked as after the attribute set member variable has been initialized. So we just have to make sure that we only call this after attribute set has become valid. So we're going to cast to Aura attribute set, and we're casting our attribute set member variable. And then we can access Aura attribute sets attribute accessors, such as get health and get max health. So we can take on health changed, and we can broadcast the Aura attribute set get health. And we can also take on max health changed, and we can broadcast. And what we can broadcast is Aura attribute set get max health. And now as soon as broadcast initial values is called, we'll broadcast the values of the actual health and max health attributes on the attribute set. Now, writer's going to tell me this can be a const local variable, so why not? We'll make that pointer const. And now broadcast initial values will broadcast our initial values. So when do we actually call broadcast initial values? That's the question, right? Because we have to make sure that we have a valid attribute set at that point in time. And we should also call this after any widgets have had their widget controller set. Well, let's go back to aurahud.cpp right here in init overlay. Now, we've created the widget, we've created the widget controller, and then here we're setting the widget controller to the result of get overlay widget controller. So when can we broadcast initial values? Well, we've got our widget controller here. We've called get overlay widget controller, passing in those widget controller params. So at this point, the widget controller does have a valid attribute set. And at this point, our overlay widget has its widget controller set, which means that widget controller set blueprint event will be called at this point. That's where we can do those things like bind to the widget controller's delegates. So only after this has happened, should we tell the widget controller to broadcast its initial values. So we'll do it right after that. So what we'll do is take widget controller, and we'll call broadcast initial values. So as long as we're setting the widget controller and binding those widget blueprints events to the widget controller's delegates, as long as that's happened first, then we can call broadcast initial values, and our widget blueprints can respond to them. So let's make sure that everything is done on the blueprint side for the system. I'm going to go ahead and run in debug mode. Okay, I'm back in the editor, and what I'm going to do is go into my blueprints UI overlay and open WBP overlay. This widget blueprint has its widget controller set to my overlay widget controller. Of that, I'm certain. But I really would like my health and mana globes to also have their widget controller set to my overlay widget controller. See, multiple widgets can have their widget controller set to the same widget controller. So here in the graph, I'm going to right click and get my event called widget controller set. At this point, I know my widget controller is a valid widget controller. And I'm going to set the widget controllers on my 2 widgets, my WBP health globe. I'm going to select that here and check is variable. And my mana globe, I'm going to select that and check is variable. And back here in the graph, now that I have these as variables, I can drag them out, both of them, and I can set their widget controllers by calling set widget controller. We made that blueprint callable. So I'm going to call that for both of them. And what I'm going to set their widget controllers to is the widget controller that WBP overlay has. So I can access that with a right click typing widget controller, and I can get widget controller and simply set it for both of these. And now as soon as WBP overlay has its widget controller set, and by the way, that's right here in init overlay in Aura HUD, it's calling set widget controller for the overlay widget right here. As soon as that happens, this event triggers off, which means we're calling set widget controller for the health globe and the mana globe. But what does that mean? It means that their event widget controller set will also be kicked off. That's because set widget controller calls this. So here in C++, we've called this function. We have not yet reached broadcast initial values. We're still here because this sets off a chain reaction. starting with event widget controller set, which calls set widget controller for the health and mana globes. And that triggers their event widget controller set to be called, which means we can go into those widget blueprints. We'll go to UI, progress bar, and open health globe. And here in the graph, we can right click and type widget controller set. And this will be kicked off as soon as we've set that widget controller here in the overlay. Pretty cool. And that means the widget controller here is valid. So we can right click, we can say widget controller, we can get that. And this is just a U object, but the cool thing is it's been set here, which means if we can cast it to overlay widget controller, we can bind to those delegates. But if I type overlay widget controller, well, we don't see anything here. And that's because back here in C++, our overlay widget controller needs to be a blueprint type, and we should make it blueprintable as well. Blueprint type means we can do things like use it as a type in the event graph. So as if we want to cast to it. And blueprintable means we can make a blueprint based on this class. So let's make it blueprint type and blueprintable. We'll do both. And for that reason, I'm going to close the editor, but I want to save selected, save all that stuff. And we'll go ahead and launch again. So we'll run in debug mode. And I'll go ahead and open up the health globe and the overlay both. And right here, I want to be able to cast it to a widget controller. If I type in cast to overlay widget controller, now I have that option, right? And from here, I can access those delegates on health changed and such and bind things to those. But we also made this class blueprintable. And for that reason, I'd like to create a blueprint for overlay widget controller and just work with that. So I'm going to go to blueprints, UI, make a new folder called widget controller. Here in widget controller, I'm going to make a new blueprint based on overlay widget controller. So selecting that, and I'll call this BP underscore overlay widget controller. And it's this class that I would like our HUD to construct rather than a raw C++ class. So back in the UI HUD folder, opening BP Aura HUD, we can set overlay widget controller class now to BP overlay widget controller. Now we're not using a raw C++ class there. And now in our health globe, rather than casting to the raw C++ class, I'm going to cast to the BP version. I'm going to say cast to BP overlay widget controller, and that way we're dealing with the blueprint. And as soon as health globe has its widget controller set, it can access the on health changed. And if we choose assign on health changed here, and hook that up, then as soon as that broadcast is made, remember in broadcast initial values, we're broadcasting on health changed. As soon as this broadcast is made, if we assign this event to that delegate, then this event is going to be called. And I'd like to assign to not only on health changed, but also on max health changed. So I'm going to type on max health changed and assign that one as well. So now we have the ability to do something when we broadcast that. And when we broadcast the initial values, we want to set the percentage for our health globe. Now we're going to be setting one and then the other, right? And typically our percent is health divided by max health. So what we'll do is we'll set the percent for both times. Each time we set the health and the max health, we'll go ahead and divide and get the percent. So here's what we'll do. As soon as on health changed is called, we can promote new health to a variable. And that way we'll set that variable. And then we'll do the same thing for on max health. We'll promote that to a variable. So for on health changed, we'll promote this and we'll call this simply health. And for on max health changed, we'll promote this and we'll call this max health. Now our health globe has both of these. And after setting health and after setting max health, we'll set the health percent. Now we want to be able to set the percent for the progress bar, but we don't have access to it here because this exists on the parent class. So we need to open that parent class, WBP globe progress bar. And we need a function to set that percent for our progress bar globe here. So we're going to make a function here on the base class. So we're going to click add function, and we're going to call this set progress bar percent. We're going to give this a float input parameter. So adding an input here, it's going to be of type float. We're going to call this percent. And we're going to get our progress bar here, progress bar globe, get that, and call set percent on this. And hook that up and just pass percent in like that. And set progress bar percent. This function can be called in our WBP health globe. So I'm going to compile here. And here in WBP health globe, after we set health, we're going to call set progress bar percent. And what are we going to set it to? We're going to set it to health divided by max health. So I'm going to hold control, drag out health, drag out max health. And I'm going to divide, but I want to do a safe divide. And that way, if max health is 0, in other words, it hasn't been set yet, or it just happens to be 0, well, then we're not dividing by 0. Safe divide will just return 0 in that case. And I'm going to take this, copy it, and paste it over here so that I can call set progress bar percent here as well. I'm going to duplicate this function call and do it there. So we're calling set progress bar percent whenever health gets set and whenever max health gets set. So when we broadcast initial values, well, we're going to call this here when max health is 0 and set progress bar percent to 0 if health gets set before max health. But if max health gets set first, then at this point, max health will not be 0. So either way, we'll get that progress bar percent set. So I'm going to compile and save all just in case we crash and press play. And now our health is set to full because we're actually accessing the real health value and the real max health value. Both of those should be 100. If we type show debug in the console, ability system, we'll see that health is 100, max health is 100. And so we see the real value there, and that is great. So this is nice because our base class globe progress bar now has a function to set its own health percent. And in our child class health globe, we can call that function, and we have the ability to do the same thing in other child classes such as our mana globe. Now, before wrapping up this video, I'd like this all to be nice and organized. So what I think I'd like to do here is I'd like to promote this BP overlay widget controller to its own variable. So I'm going to drag off of it, promote a variable, and call this BP overlay widget controller, and set that. And then I can organize this a little bit better. So instead of just dragging off of the cast, I now have this variable here that I can use. I can control drag it in and hook that up there. I can control drag it in and hook it up there. And we don't need these all connected like this. This one needs to be connected, but these two don't. And I can also organize this all with a sequence. So why don't I just drag everything off to the side just a bit. And after event widget controller set fires off, we'll do a sequence. The first thing we'll do is set the widget controller after we've cast it to the blueprint version. And then for then 1, we'll bind to on health changed. And then we'll have a then 2 where we bind to the max health. Like this. And that way things are organized. And up here, this will be put in its own comment where we'll say set widget controller. And I'll add a reroute node to it. And I'll put a comment on the second one here where we say bind to on health changed. And I'll put a reroute node there. And I'll comment the third one and say bind to on max health changed. We'll put a reroute node on that one as well. And if you like, you can click on the comments and change the comment color if you want. For example, if you want to bind all your delegates and have those share the same color, say a light green, for example, you can do that. You can also drag that color up here to save it. And then you can select this comment and choose that save color if you want your delegate bindings to all share the same color, for instance. That way you can look at it and know that those are binding to some delegates. Okay, so now we're successfully broadcasting from our widget controller and binding to those delegate broadcasts here in our widgets so that we can have actual real values shown here on the screen. And we're going to get to test that and also set this up for the mana globe as well in the videos to come. So great job. I'll see you soon. Welcome back. Now that we have our widget controller, I'm going to go to AuraHUD here and just take a look at an overlay. We know we have a widget controller on our overlay widget. And the overlay widget has a handle to the widget controller. It has a pointer variable, and we can access that. We've seen that we can even access it from Blueprint. Now, the widget controller doesn't know anything about the overlay widget. All the widget controller knows is that it has access to the 4 key variables. That's how it's going to access data to broadcast to the widget. And when we say broadcast to the widget, we are talking about delegates, because delegates are a great way to have one-way dependencies where our widget controller doesn't know about the widgets that it's broadcasting data to. The widgets know about the controller. That's the way that it goes. So our